Okay, so we have the existence and uniqueness theorem for linear nth order differential equations. So this theorem answers the question of when does an initial value problem have a solution? And when does it have more than one solution? So the existence talks about whether or not a solution exists, and then the uniqueness part is whether or not that solution is unique, or are there more than one? So the statement of the theorem reads, if an initial value problem, so here's an initial value problem, has the properties that each of the coefficient functions is a continuous function of x, and also f is a continuous function of x on some interval. And it also has the property that an of x, so that's just the coefficient here of the highest order term, if this has no zeros on the interval I, then the initial value problem has a unique solution. So that means then that if these conditions are not satisfied, it's possible that there's no solution, or maybe more than one solution. So for an example of that, let's look at this function or this ODE that we had earlier, y prime equals y squared. Now recall that this is nonlinear precisely because of this term right here. You're not allowed to have the dependent variable squared or raised to any other nonlinear function for it to be a linear ODE. And we checked by substitution that this formula, 1 over c minus x, solves this equation. And so here's a bunch of curves from this one parameter family of solutions, and these correspond to different values of c. And now, if I were to pick something for an initial condition, like say y of 1 is equal to 2, so here's y of 1 is equal to 2, so that's x equal 1 and y equal 2, then that would single out this particular solution curve right here. Now, what if I were to choose so that was y of 1 is equal to 2. Now, what if I were to choose something like y of 0 is equal to 0? Well, that would be passing through this point right here. And you can see that none of these curves pass through that particular point. However, here's a curve that does. So this is the function y is identically equal to 0. So for identically equal to 0, I've got that triple bar there. And you can check that this function satisfies this equation as well, because the derivative of 0 is equal to 0, and 0 squared is equal to 0. So the derivative of 0 equals 0 squared. So this is, in fact, a solution to this initial value problem, y prime equals y squared with y of 0 equal to 0. However, note that this guy here is not given by any value of c in the general solution. Now, this kind of thing can only happen for nonlinear equations. So we will see that in general, nonlinear equations are hard. We're only going to learn how to solve maybe one or two types of nonlinear equations, and they'll be pretty simple ones. In general, we don't touch nonlinear equations in this class with a 10-foot pole. We will just be sticking with linear, which is kind of why the name of this course is Linear Analysis. Let's look at one other example of how the theorem might work. So here we have the differential equation x times y prime is equal to 4y, with the initial condition y of minus 1 is equal to 1. So what happens here? Well, it turns out that the general solution for this equation is y equals cx to the fourth. So when we choose the initial condition y of minus 1 is equal to 1, so there's x equal minus 1, y equals 1. We're going through this point right here, and so this selects this particular solution coming through right here. However, at this point, different things can happen. So, for example, if I take the function y equals, let's have it be x to the fourth for x negative, and then minus 2x to the fourth for x non-negative, like this, then that equation, that curve would carry on like this out the other side. So what's going on here? Because I could have easily changed this and had this be, say, 1/2, in which case it would have continued on here like this. So this is a situation where we have non-uniqueness. There are multiple solutions. So can you spot the feature of this differential equation which allows it to have this property? Okay, so let's see. What is it? Well, the coefficient of the highest derivative, which is just y prime in this case, it has a 0 at 0. So the theorem tells us that the function will have, there will be a unique solution on some interval around -1, and it turns out that that interval is just going to be something out here on the negative side. And that's because if we zip back to the statement of the theorem, we need to have it be the case that the coefficient is never equal to 0 on that interval. And you say, oh wait, I know a fix for that. I'll go back to this equation right here, and I'll rewrite it by dividing the x over to the other side, so it looks like dy dx equals 4y over x. Aha. And then you say, okay, so how is this violating the theorem now? Well, it's not violating the theorem because now the coefficient function of y is not continuous at x equals 0.